Now we are going to see some statistics. In order to do so, first I need to introduce you to none and inf. Okay, these are specific values of numpy, which correspond to inf corresponds to the positive infinite plus infinite, and none corresponds means not a number. Okay, not a number is something that is usually the result of a function operation which is outside the domain of this function, or of an undefined limit. And this inf is sortable, meaning that of course minus inf is less than any other number and plus inf is going to be greater than any other number, but none is not sortable. We cannot know if the result of any of these operations is going to be greater, less, or equal to any other number. Okay, so it is not sortable. We will see some examples using this part over here. This is all a load of prints with many operations. I'm using in all this stuff. I'm using this print, okay, and this is going to be a string, the string that I'm printing. This string is a formatted string. I'm going to explain here what a formatted string is. A formatted string is a string that may have several things inside, okay, several strings. But if we write something between curly brackets, then this is going to be computed and written. In this case, if I write the equal sign afterwards, then it's going to be written this part, okay, and then it's going to be computed, and then it's going to be written the result of this computation. I hope it's more or less understood. So the result of doing this, the result of this line of code would be this thing over here. Notice that np.log0 is what I have here. Then we have the equal sign, which has the same format and the same number of spaces as the one that I have here, and then the result of this operation, of this np.log0. Okay, and now let's go with nuns and infs. So the result of the logarithm of 0, this is going to be minus infinite, because there are the limit, the only domain, yes, the domain of the logarithm function are numbers strictly greater than 0, and for 0 we have that the limit when these numbers go to 0, approximate to 0, the result is a negative number, more and more negative each time. So in the limit, when we get to 0, what I have is minus infinite, okay, which is minus inf in this case. If I try to compute the logarithm of minus 1, what I obtain is not a number, because minus 1 is outside the domain of the logarithm function. But infinite works pretty well with known limits. For example, if we try to compute the exponential function of minus infinite, we know that this result is going to be 0. And in the same way, if we try to compute the exponential function of plus infinite, this is going to be infinite, of course. If we try to compute 1 over infinite, this is going to be 0. Okay, and this works exactly the same for any number over here, except not a number, and plus or minus infinite the denominator, sorry. Of course, what we have is that if we try to subtract any number to infinite, this is going to be infinite, and if we add any number to infinite, the result is also going to be infinite. If we multiply infinite by any number, then if the number that we're multiplying it is positive, then it's going to be a positive infinite, and if it's negative, it's going to be a negative infinite. And infinite is going to be greater than any other number, so this is always going to be true for any number that I have here, except for not a number. If we try to compute infinite divided by infinite, then the result is going to be not a number because, well, this is not a defined limit. Depends on the size of these infinites. Okay, if we try to do it not numerically but theoretically, then we would have to obtain something, whatever it is, which is, it may be a plus infinite, minus infinite, or zero, or a specific number, whatever. Okay, and then when we try to do the same operations as we did before with infinite, if we try to do them with not a number, then the result is always going to be not a number. Since we don't know which number is this one, then if we add any number, the result is going to be still not a number. If we multiply it by any number, the result is still going to be not a number. And since we cannot order it because we don't know this number, then this thing over here is going to be false, okay, because we cannot say if this number is going to be greater or less than 0. This is also true for infinite, so because we don't know which is the result of this thing, this is going to be false, true also. But even in this case, if we try to know if this is equal to, okay, so this is to check if these two things are equal, okay. So a not a number, if we try to see if this is equal to a not a number, the result is going to be false. And you will say, but how is this possible? Since this thing over here is the same as this thing over here, of course they are the same. Well, they're not, because numpy knows that we don't know which number is, and the same applies for this thing over here. So in general, we cannot compare not a number with any other thing. What we can do is to check if a number is not a number, is to use this check. So in this case, what we are checking is if a number is not a number, not is equal to a not a number, okay, because this implies a numeric value, and this implies a computational a computing store, okay, a constant, let's say, okay, and np.num works like a constant inside numpy, and this only checks if we are using this constant. Although there are other functions like np.isNum. Okay, so if I have np.num, I hope this works. Yes, and the result is true because this is going to be none, is none, and the same applies for isinf. I think it's exactly the same for isinf. Yes, it's inf. Isinf np.none is going to be false, of course. Okay, this is false, but if I try to write this thing, then this is going to be true. Okay. And this thing that I have it just for this for non-arrays, I mean these are not arrays. These are not one-dimensional or two-dimensional arrays. These are just numbers, okay, scalars. Well, this also works for arrays, okay. And we will see now for the statistics. We will see that not the numbers are important. Well, and infinites too, of course. So we will see some of the statistics that we can do with numpy. We can do order statistic, averages, variances, and we can compute correlations. Some of the versions of these things over here have a version to exclude the not numbers from these statistics. And for more information, you can see this link over here. Okay, so if you see this link here, you can find all the statistics, order statistic, averages, correlating, histograms, etc. Okay. So we are going to see some examples. First of all, I'm going to generate a random array formed by five 5 numbers. This is a one-dimensional array formed by 5 numbers in the interval 0, 1, okay, with uniform distribution, including 0 and excluding 1. Okay, and this is the result, which can be seen here. Okay, these are the 5 numbers: index 0, index 1, index 2, index 3, index 4. And now I'm going to insert some nota numbers and some infinite in this array, well, in a copy of this array. So I'm going to copy this array, because if I do this and then I do these things over here, I'm going to change this array, and I don't want to do that because I want to compare statistics between this array and this copy with the nota number and the infinite. Okay, and the result is the following. Notice that we have five elements. The index 2 is going to be this part over here, and the index -2 corresponds to this element over here. Okay, so I'm assigning not a number to the third element and inf to the fourth element. Okay, and now I'm going to sort these two arrays to let you see what happens. So when I sort this the X array, what I obtain is an array with the sorted values from in ascending order of this X of X. Okay, and if I try to do the same with Y, well, the result, what it does, in order to do something, because nota numbers are non-sortable, what numpy does is to put them at the end of the array. So they are going to be at the end of the array. But the rest is already sorted. So we have the inf is going to be at the end before the none, because this is the largest value. Infinite is going to be larger than any of these values over here, and these are the first three elements are exactly the same as in the previous array. Well, no, I'm sorry. The second first elements are going to be the same as in the sorted X, the sorted version of X, and since we have deleted this element over here, okay, we have replaced this element, and we have also replaced to this element over here, then I have I have this this is going to be the third element of the sorted array for Y, and this is going to be the third element of the sorted array for X. And the fourth element is going to be 0.77 and infinite in the case of Y. So if I try to do the order statistics, which are basically minimum, maximum, quantiles and percentiles, then what I have is that the min function of X is going to return the minimum value of this array. If I try to do the same with Y, this is not going to work, because I have another number here, so I cannot find the minimum of this array. But if I call this function, which is nunmin is going to return the minimum value of the Y array, excluding all the not a number values. Okay, so in this case we have the same value as before. We have that the minimum in both cases is 0.09 for one, blah 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 blah. Okay, if I try to do the same with the max function, then I'm going to obtain 0.85 blah 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 with for X, and I'm going to obtain infinite. Well, I'm going to obtain not a number if I don't do anything, and non-max is going to return inf. Okay, because this is going to be infinite. The largest value is going to be infinite. If I try to do argmin with these two array, argmin is going to return the index where you can find the minimum value. Okay, and argmax is going to return the index where we can find the maximum value. So argmin is going to be the position of this element in the original array here, and this value is in the last position, which is index 4. So argmin of X is going to be 4. Great. If I try to do the same with y, this is not going to give me not a number, but this is going to give me something weird. So we are not going to make a lot of, we are not giving much attention to this result, although noticing that it is false, okay, this is not right. And in this case, when I use non-argmin, then this is including then not a number, okay, and the result is also 4, which is here. It was the last element, okay. So this is good. The result should be the same in both cases. If we try to compute the quantile of these two arrays, I'm going to find that the 25% quantile is going to be given by this number, okay, which is exactly this number over here. In case we don't write exactly, well, this is 0.25, okay, this is the 25%. You have to notice that this is going to, if we write here quantile x0, the result is going to be this number over here, and if we write x1, the result is going to be this is going to be 0, okay, the quantile for 0, and this is going to be the quantile for 1. And in between 0 and 1, we have, in this case, 1, 2, 3, 4, 5 elements. So the first element is going to be the 0 quantile, the last element is going to be the 100 quantile, and the rest are going to be the other 3 points that we know are going to 3. This is going to be the one in between, which is 50%, this is 25%, and this is going to be 75%. If we don't use 0.5, 0.25 or 0.75, then it's going to be a linear interpolation between these numbers. Yes. And now, if we do exactly the same with y, with the y vector, I have to use non-quantile, because in other case I'm going to obtain not a number, and this is going to be the result, which is not the same as the previous one, because in this case, since we are not considering not a numbers, now we don't have 5 elements, we have only 4 elements. So this element is going to be the 0 quantile, and this is going to be the 100 quantile. Well, the 1 quantile, okay? And this would be the 33.3 and 66.67 or 66666, and this is 33.33333. So to obtain the same result, notice that I have to have the the quantile 0.33333. Okay, this is going to be the result, which is exactly the same as here. And this is for sorting statistics or order statistics. If we want to do average and variances, well, I'm going to make this example over here. In this case, I have defined this X matrix, okay, which is a 2D array formed by random integers between 0 including and 10 excluded, so it's going to go from 0 to 9, and the shape is going to be an array with 5 rows and 3 columns. And this is the result, okay? This is the array with 5 rows and 3 columns. And now I'm going to insert NAM and inf, okay? And in order to do so, first I need to convert this X array over here, which is of type integer, okay? These are integers, so the result, and we have not dots over here, so these are integers, and this is an integer array, okay? The type is going to be int 64. But if we insert not a number or infinite, and we don't do this before, then we are going to have an error. Okay, we are going to have an error because we are going to try to insert a float or floating point numbers, because these are associated to floating point numbers, to an integer array, and this is going to give an error, and that is why I have to do this before. Okay, so if I don't do this, then this is going to give an error, and I will do the example over here. Yes, here. So I do this, and I am going to delete this. Just I'm going to do the copy just as before, and I try to repeat this, and when I try to do this, I have an error which says value error, cannot convert float none to integer, because none is considered a floating number, and this is an array of integers. Okay, if I print x.dtype, the result is going to be int64. Okay, this is the type of integers that we're using here. Alright, so we have this here. Once I have defined these two-dimensional arrays, notice that I have changed this element over here and this element over here. The rest is exactly the same. And now I'm going to compute averages and well, things related to averages and variances. You can find the average, the weighted average. You can also compute the median instead of the mean. You can compute the standard deviation just like here, or you can compute the variance and some other things. So in order to know which ones to use, you have all these functions over here. And now we have the results. So if I try to compute this over here, the result, well, I'm using exactly the same as before. Okay, I'm printing the operation and the result just in the same line. So if I try to compute the mean of this x variable, which is a two-dimensional array, in the zero axis, the result, notice that I'm using the zero axis to compute the mean. So remember that the zero axis are the rows. So I'm computing the mean in the rows, not for each row, but I'm using the rows to compute the average of these columns. Okay, so I have column 1, column 2, and column 3. And that is why the result is an array, a one-dimensional array with 3 elements, which are the averages, the means of these 3 columns. If I try to compute the same with axis equal 1, then the result is going to be, now axis equal 1, remember that is for columns, so now we have, we are going to make the average in each of these rows, so it's going to take all the columns for each row. Okay, so now I have, well, if the point is that if I try to do the same with y, with a two-dimensional array with nums and imps, if I try to do this the same with y, then what I obtain is that the first column is going to give me the same result because it's exactly the same. The second column is going to give me another number because I have here another number, and the third column is going to give me an infinite because here I have an infinite. So if I try to do the average with infinite over here, the result is going to be infinite. So in order to change this, I'm going to compute the non-mean. That non-mean is going to take out the not a number values. So in this case, the first column is going to give exactly the same result. The second column is going to be a slightly different result as in the x case, because I am not using this element over here and I'm dividing by 4 instead of by 5. Okay, so this is why we are obtaining 5.75 instead of 5.8. Well, and in this case we are adding 7, 4, 6, 5 and 7 divided by 5, and in this case is 6, 4, 5 and 7, 7, 4, 5 and 7 divided by 4, and this is the result. Okay, and in the last column, since we are only dealing with nums, if we have an infinite, we're still going to obtain an infinite here. It doesn't matter if I use the non-mean. I can do exactly the same for the standard deviation. The standard deviation, if I try to compute it for the two-dimensional array x, this is going to give me no problem, all the standard deviations. no problem. And for y, this is going to give me not a number in the third row, so the third element is going to be not a number, and it's going to give me an infinite in the last row. So the last element is in this case we obtain also a not a number, okay. And why are we obtaining a not a number here? Because we are dividing, in order to do this, we are dividing infinite by infinite, because the mean is going to be infinite, and when we divide it by, you know why. It's not by division, it's by subtracting, I'm sorry. So that's the problem, okay. So I have here, in fact, I have this one-time warning that is showing me this problem, because I have an invalid value encountered in subtract. So it's trying to subtract the value, which is infinite, minus the average, which is also infinite. So infinite minus infinite is exactly the same as infinite divided by infinite, which is not a number. Yes, the same thing happens here, okay. This is exactly the same. In this case, we are obtaining here, instead of not a number, we are obtaining 1, because we are using non-std, and non-std is going to exclude this not a number here. So when we compute the standard deviation of these two numbers, 0 and 2, well, the standard deviation is going to be 1, because the mean is 1, etc, etc. So we have here 1, and this not a number is exactly the same as we had before, just exactly the same. And that's it. And the last but not the least, I'm going to talk about reshaping arrays, with what we are going to do a lot, okay. We are going to make a lot of reshapes and a lot of flatten and ravel and these things, and I'm going to show you what they do.